In this video we're going to look at the relationship between line shapes and peak models. In particular, we'd like to understand how a choice of line shape can influence the stability of a peak model. We have two examples of line shapes that are approximations to peaks that involve Lorentzians and Gaussians. The LA line shape is a Voigt function that is formed by a numerical integration of a Gaussian with a Lorentzian, whereas the GL line shape is an approximation to a Voigt function that is formed by the product of a Lorentzian with a Gaussian. On the face of it, looking at the results of these two peak fits applied to the same data, the differences are minimal, and so one might conclude that there is no real advantage to choosing one over the other when fitting these types of data. However, the difference between choosing a Voigt function and a GL line shape only becomes obvious when you start to look at data with poorer signal to noise and attempt to fit that data using a peak model of this form. When thinking about line shapes, it's worth considering the origin of these line shapes and going back to how a hemispherical analyzer produces such a line shape. Now, if we consider a hemispherical analyzer where a sequence of electrons of a range of energies enters via a narrow entrance slit in a para-axial direction, then this simplified form of a spectrum would be produced by the dispersion of the hemispherical analyzer across the exit aperture, and in particular signal that is sampled by a detector that is located at the exit aperture then produces a spectrum, and this is the spectrum that we fit with our line shapes. So this particular shape that appears in the data system is the consequence of integrating this signal that is arriving at the exit aperture. And if we consider the shape of a Lorentzian line that arrives at the exit aperture, if the exit aperture is a narrow detector slit and we only sample data through this slit, then rather than seeing the pure form of the line shape or the underlying line shape, what we see is signal that is an integral over an interval. And so rather than seeing the pure form of the line shape, what we see is a distorted shape that arrives in the data system that we then have to analyze using a peak model. To a certain extent, we can approximate this idea of integrating signal by a convolution. So this is a Lorentzian that is convoluted with a Gaussian representing the response of this aperture here and the detection system, and this is what we would expect to be the best approximation to the photoemission signal that we actually receive in our data system. However, historically we've used GL and SGL line shapes as a means of approximating this Voigt function on the basis that these are computationally efficient compared to integration that is of this form to construct a line shape. So we've got a GL line shape is the product of a Lorentzian with a Gaussian, or the SGL, which is the sum of a Lorentzian with a Gaussian, and we have these mixing coefficients that determine how these two functional forms are blended to produce a line shape. And here we see a range of such forms that are constructed using a GL line shape and the corresponding sequence for the SGL line shape. And you can see that the difference between these two by eye seems to be very minimal. However, the consequence to fitting is significant. And we can illustrate the influence of the line shape on peak models if we consider a data set where the signal to noise is far worse than the data used to construct the peak model. Now, in reality, the data used to construct the peak model is the sum of these data. The measurement of this sample was performed by performing a sequence of measurements at a very fast rate and then producing a number of such spectra as a consequence of repeating the same measurement with the acquisition time that will be typical of what you might expect for an XPS measurement. So this is a way of distributing information over time into different VAMAS blocks, and it gives us a data set against which we can test this peak model. So the data of interest are these carbon 1s, and I'll copy these into a new VAMAS file, and then I'll make a further copy and these will be offset in a new column by virtue of the element transition field. And the idea is this first one I'm going to use as my LA line shape, and the second column I will adjust the element transition field to indicate that this is going to be the GL line shape. And the idea is to propagate each of these peak models to these columns, and the columns are identical. That is to say that I've got the same data in each one of these VAMAS blocks, so you can only see them if I offset the data. So this is now the test bed against which these peak models will be assessed, and to do that I'm going to cascade the windows so I can see the data sets, and this one is tile displaying the peak model that involves the LA line shape. I've got a column selected in the other file, and I right click and then I'm going to propagate, and I will propagate and fit. Now it's asking me whether I want to propagate, and that's because I changed the element transition field, and yes, I do want to propagate, so I'm going to press yes. So that generates one column that now has a peak fit that's based on the LA line shape. So if I select the second column and then right click over the data that has a peak model that involves the GL line shape, I'm going to propagate regions, components and auto fit. So I then say yes. So this means that these two columns represent a set of spectra that, when summed, were fitted using the peak model involving either an LA line shape or a GL line shape. Now if I overlay these in the active tile, the first column, these are peak fits that only involve LA line shapes. And we end up with a set of peak models and residuals that are certainly acceptable residuals, and the peak model shows some variation that you might expect as a consequence of there being noise in these data. Now when I overlay the GL model, the results are very different. You can now see there's quite a significant spread in these peaks, and the reliability of a peak model based on the GL line shape fitted to these data is nowhere near as consistent as you obtain when you have a line shape that is based on a Voigt function. And this is the primary reason why the LA line shape is preferred to a GL line shape.